Welcome back to Separations and Mass Transfer Operations. It's been a while since we last covered some content, and that topic last time we got together was cross-current liquid-liquid extraction. And to review that, I want to go back to the course notes from a while ago. So this is a process flow diagram for a three-stage process. This is a problem that we've solved before. I just want to quickly go over the solution procedure again. Remember, for this problem, we started with everything in the green was specified already, and everything in the gold was stuff that we had to solve for. So the procedure with a cross-current LLE process is to go stage by stage if you can. So on the first stage, you start by finding the mix point is the first step always. So you figure out by doing a material balance on the two streams coming in what the mix point is, and you draw your mix point inside the two-phase region, wherever it happens to be. And then from your mix point, you draw a tie line, and that tie line will give you the compositions of your extract and raffinate phases. So each point has three compositions for you to read off of the diagram, and those can go in the diagram there. And then the last step for each stage is to do material balances again to figure out what the flow rates R and E are for each stage. And then once you have the raffinate solved for, so flow rate and composition, if you know what the solvent flow rate is to the next stage, you can just repeat the process over again. So for stage 2, find the mix point, draw your tie line, figure out the compositions of the raffinate and extract, then do material balances again. So cross-current extraction processes were rather straightforward because you can just go stage by stage doing those three steps repeatedly until you achieve your desired goal. I pointed this out before, but I wanted to point it out again. If you look at what the compositions of your extract are, so extract number 1, for instance, has 32% acetic acid. My extract number 2 has 20% acetic acid. And I didn't write what my composition of acetic acid in my third extract stream was, but this is the point down there, and it looked like it had about 5% acetic acid, so 0.05 AA. And this trend is reproducible, so you see this all the time in cross-current liquid-liquid extraction processes, that the solvent stream, the extract, is becoming more pure the more stages that you add on to this process. So the thought is then, why would I send pure solvent to each stage? Because that seems kind of wasteful. So I'm sending 200 moles per hour of pure solvent to stage 1, 2, and 3. Whereas this solvent, coming off of the nth stage or the third stage in this process, it only has 5 weight percent acetic acid. So therefore, it's still relatively pure. So instead of just extracting this and then wasting it and then having every stage have an extract stream, the idea of countercurrent liquid-liquid extraction is to send my extract from the stage after to the stage before. So same thing with extract 2. This extract 2 would replace the need for an S1 stream. And then all I have to do is feed fresh solvent in once in the diagram in the nth stage or the last stage, and then I have a single extract stream at the end of the process. So I'm going to go back to my notes for today, and I'm going to pause the recording really quick, and then I'm going to draw a process flow diagram for a cross-current cascade. All right, so I've just done 3 stages. You could obviously do more if you wanted to. To the first stage, so I'll mention the convention is to number any way you want, really. I think left to right is easiest, but there's no reason why you can't go top to bottom like we did for absorption stripping, because liquid-liquid extraction oftentimes occurs in a column, just like absorption stripping. So it's just personal preference why I choose to write these diagrams left to right, but it helps remind me that it's a separate process. So as typical, we usually know what the feed is. So we know what the feed flow rate is. And another name for the feed stream, instead of F, I could call this F, or I could call this the raffinate of stage 0, because it's coming off of, quote, the 0th stage. Typically, I know what the composition of all 3 components are of the feed. So I'm going to write that. Brown is going to be my known variables. and red, I will do my unknown variables. So oftentimes, again, I always know what the feed is and what's in it. And typically in my process, I know what my what composition I want the extract to be. So I'm going to go ahead and suppose, for sake of argument, that I know what one of the compositions has to be in this exiting raffinate stream. Now you'll notice I'm following the convention where the stream gets the subscript of the stage that it comes from. So I'm going to fill in some other variables here. R1, I don't know what the flow rate is of that. That problem wouldn't necessarily specify that. The problem would also not specify what the compositions are of that stream. So R2 comes off of stage 2. This is the second raffinate. And I have a certain mole fraction of all the three components from stage 2. And then, although I know what the composition of the third raffinate is, I don't know what the flow rate is. So I'll just call that R3. So again, red is unknowns, brown is knowns. And then on my solvent side, I feed some amount of fresh solvent. And I'll put fresh in quotes here because even though it's fresh, it doesn't necessarily mean pure. It's usually pure-ish. So I'll say that, pure-ish. And I know what the flow rate is because that's one of my process variables. And I also know what's in it. So I'm going to call this stream, another way to call it instead of S is E of the n plus 1. So that's going to be the same thing. Same variable. I'll try and use S and F, but for some of the equations, it makes sense to call this E of n plus 1. You'll see what I mean in a minute. And my composition is also known. So Xi En plus 1. And that is necessarily all I know. So I don't know anything else in this diagram. So I've got E3, Xi, E3, E2, Xi, E2, and E1, Xi, E1. All right, and importantly, the same relationships will hold. So importantly, I can say that streams coming off the same stage, coming off a given stage, are in equilibrium, And remember what that means is that their compositions are connected with a tie line. Compositions connected with a tie line. Then the other important relationship is that any streams coming into a particular stage must be balanced by streams coming off of that particular stage. So again, these are the same two key relationships that we've seen for every separations process. Anything coming off a stage is in equilibrium. Everything coming in is in material balance with everything coming out. Now, this type of problem is more difficult to solve because I don't have any stages that have a 0 degrees of freedom. So I'll show you what you mean. In stage 1, for example, if I tried to start there, if I tried to do my same algorithm that I was using, I'd want to find the mix point. However, I can't necessarily find the mix point because that requires that I know both streams coming in. So here I could say that the mixing point of stage 1 is F plus E2. So what's coming in must equal M, must equal what is coming out. So R1 plus E1. And in this equation, the only thing I know is F. I don't know E2, R1, or E1, or M. So there's too many unknowns in that equation to solve for it. And just because I know what's in my feed, if I know all the components, I still don't have enough information to solve for all these flow rates because I don't know any of these compositions either. These are all unknown. So stage 1 is out as a starting point. Similarly, stage 2 is out as a starting point because I don't have any given information in stage 2. Everything is in red. So my last possibility is stage 3. And again, I could start with trying to perform a material balance to find the mix point. But I would run into a similar problem. So I could say S plus R2 is equal to M3 is equal to E2 plus R, E3 plus R3. But again, I don't know what the flow rates R2, E3, or R3 are. But then what I could say is that, well, since I know that the composition of the third raffinate stream, I could say that that is in equilibrium with the third extract stream. So I could try to do that, and I'll show you what that would look like on the equilibrium diagram. So I'm going to pause quickly. So just for sake of argument, I put some variables for the variables that I'm assuming are known here. So I remember I know what the flow rate of the solvent is, what the composition of the solvent is, and I have one specification for the third raffinate stream. So this is a balance on stage 3. So again, these numbers are strictly arbitrary, but if I said that my raffinate 3 stream had 15% ethylene glycol, I've plotted that on my ternary diagram. So all I have to know is that it's 15% ethylene glycol, which means that it lies somewhere along the 15% ethylene glycol line. And because it comes off of a stage, it must be on the equilibrium diagram. Because it must be in equilibrium with something, remember I have two options for where this is. It could be either on the left side or the right side. And I know it's on the right side because this is my raffinate side. So it's the water-rich part. So knowing that it's 15% ethylene glycol and that it comes off of a stage allows me to say that it must be in equilibrium, and therefore I can get the other two compositions for this stream. So I could say that it's 75% water, and that would mean that it's about 10% furfural. So not being super careful, just meaning to illustrate this point. If I connect this point with a tie line, because remember it comes off of a stage, so therefore anything else that comes off of that same stage has to be in equilibrium, I can draw what my extract compositions will be. So this is my E3 stream, is 5% ethylene glycol. Let's see, 92% furfural, and the last 3% remaining would be water. So do I have enough information to solve this stage such that I can continue? So remember, I've got R2 here, and I've got XEG R2, X water R2, and then I won't say count the variable for furfural. I'll just say it's 1 minus ethylene glycol R2 minus X water R2. All right, so pause the video here and do a degree of freedom analysis from this point to see if you can solve. So counting my unknowns, E3 is one unknown, R2, the flow rates, E3, R2, and R3 are all unknowns. Then the composition of ethylene glycol and water. So I've got 5 unknowns total in this stage. And if I think about the equations that I can use to solve for those unknowns, the only thing I have is the 3 material balances. I don't have any equilibrium relationships because I've already used that information in linking these compositions. So by drawing the tie line and figuring out what those compositions are, I've used my phase equilibrium relationships. This leaves me with 2 degrees of freedom, and that means I cannot go forward with solving it. So it appears like we're at an impasse here because I've tried all 3 stages. None of them have 0 degrees of freedom. So where can I go to start? This is why liquid-liquid countercurrent extraction problems are more difficult than the cross-current, because I have to do a pre-step first. In the next video, I'll show you that the idea here is instead of solving individual stages, what I'm going to do is just draw a big box around my whole process, all the stages. And this allows me to do a material balance on the feed, the incoming solvent, and the outgoing raffinate and extract streams. So by doing that, I can make some solutions. I can start solving for things, and then that'll help me clear up what some degrees of freedom are. That's the end of this video. Next video, we'll do the practice problem.